Hello, everyone, and welcome to online lecture 18. That's the t-test for dependent samples. So we've talked about the z-test, and we've talked about the t-test for a single sample. Today we'll move into t-test for dependent samples, followed by, next time, t-test for independent samples. So before we jump into the t-test for dependent samples, though, let's just take a brief moment to remind ourselves about the z-test versus the t-test for a single sample. If you recall, both compare a sample mean to a population mean. Now we're going to leave that world today. We're no longer going to be comparing sample means to population means, but that's what those two compared. The population mean, the mu, is known for both. Something else we're going to leave behind today. We're no longer going to know mu, but they are known for both of these. For the z-test, the population variance is known. In other words, we know sigma or sigma squared or sigma of x bar. We know the variance or the standard deviation or the standard error of the mean for the population. For the t-test for a single sample, the population variance is unknown, which means we're either given raw data or we're given some form of S, like S or S squared or S of x bar. Okay, so that's where we've been. Let's talk about interpretation of t-tests. This is actually true for both z and t-tests, and technically it's going to be true for all of the tests we talk about after this. Okay, so when we're doing a hand calculation, I know that's all we've seen so far, hand calculations, but we'll soon see SPSS interpretation as well. So when we're doing a hand calculation, to reject the null hypothesis, the calculated t-score needs to be more extreme, further in the tail than the tabled value. Okay, so if you think about your table as either the z cutoff score or the t cutoff score, or you can think of it as the z tabled score or the t tabled score. So think about that. And then we have a t-score or z-score that you calculated that we want to compare. We want the one that you calculated to be more extreme further in the tails than the table value. Okay. So if you think of a normal distribution curve or something similar to that, we want to be further towards those tails, further out from the center. Another way to think of it is that you have a number line with a 0 in the center, and 1, 2, 3 going out to the right, and -1, -2, -3 going out to the left. Again, we want to be further away from 0 with our calculated score than what's in the table. Okay. So what's the exception to this rule? Now that we all have the rule straight, what's the exception? If you have a one-tailed test with results in the opposite direction of your alternative hypothesis, you will not reject the null. So in other words, if it says that this mean will be higher than that mean, and it turns out to be not true, that really it was the other way around, it said A would be higher than B and B was higher than A, you won't reject the null, regardless of how far away you are from the center. Okay. So now let's talk about this t-test for dependent samples or means. Now you're going to have two scores for each person. It's a repeated measures design. In other words, you're comparing each person to themselves. Now it's basically the same procedure as the t-test for a single sample, except we're going to use different scores. And we're going to assume that the mean of the population difference scores is 0. In other words, we're going to look at the differences between before and after, or between condition 1 and condition 2 for the same people. And we're going to assume that in the population, there'd be no difference. So we're looking for something more than that. We're looking for an important difference. Okay. The sample distribution of the different scores or values may not be normal, but we are going to assume that the population distribution of the different scores or values is normal. That's an important assumption. And it's very similar to the one that we use for the t-test, right? We assume that the population distribution of the values was normal. Now it's just the difference values. And you're going to see that pattern throughout our discussion of the t-test for dependent samples, that now we're talking about different scores and difference values. Okay. So the first step, the very first step you want to do when conducting a dependent samples t-test is to calculate the differences between each pair of scores and the mean of the different scores. Then you will no longer need the original data. Okay. All right, so let's take a look at that. If these are our before scores for each of our 5 participants, and these are our after scores for the same 5 participants, what we would do is just subtract. Now we could subtract before minus after, or we could subtract after minus before. And really that decision depends on the research question. In this case, I expect that my after scores are going to be higher. So I'm going to subtract after minus before. If I thought my before scores might be higher, I might go ahead and do it the other way. But honestly, it doesn't matter as long as you know which direction you're subtracting. Okay. All right. So I'm going to start off. 6 minus 8 is negative 2. 9 minus 6 is 3. 8 minus 2 is 6. 7 minus 1 is 6. And 6 minus 4 is 2. Okay, so now that I have my different scores, I can get a difference mean. So the 2 and the negative 2 add up to 0. 6 and 6 add to 12, and 3 is 15. 15 divided by 5 scores gives me a 3, or 3.0000. Now at this point, I no longer need the original data. I can throw that away. In fact, it's helpful sometimes to put an X through it or do something to just remind yourself you're no longer using that information. Okay. Now we're going to calculate the variance for the difference scores. So we're going to take each difference score minus the difference mean, square it, and then add up those values and divide by our DF, which again is n minus 1. Or SS over DF. Now you might notice that whereas in the past I used X's, now I'm using D's. And I'm using D's to remind myself that I'm only using difference scores here. I technically could run it using this. As long as I remembered that I was using difference scores, I could use the same formula for variance that I have used all along. But I like this one on the left because it reminds me that I'm only going to use different scores. So the variance of the different scores equals SUSAD. Subtract, square, add, divide. And we divide by n minus 1. So again, take each score minus the mean, We square each of those values. So we would be doing step 1 and 2 here 5 times. Subtract 5 times, square 5 times, add only once, and divide only once. Okay. Now that we have that value, we can go on and calculate the standard error of the difference mean, or the standard deviation of the distribution of the difference means. So we're going to get our SEM. Okay. So if I have a variance, if I have an S squared D, which is what I just calculated, then I'll use this formula on the left. If I just have a standard deviation for the different scores, I'll use this formula on the right. They're really saying the exact same thing. One on the left and the one on the right are exactly equal. It's just a matter of convenience. If I have variance, I take the square root of it to get standard deviation. Okay. So that's the standard error of the difference mean, or SEM. Finally, we calculate our t-score. We take our difference mean minus our population difference score, or population difference mean, I should say, over the standard error of the difference means, with a DF of n minus 1. Now, if you recall, we were assuming that mu d equals 0. That was one of our assumptions right at the beginning, which means the top part is always going to be difference mean minus 0, or difference mean. The bottom part will always be our standard error of the difference means. And DF will always be n minus 1. Okay. Now this, like the other example that we went through with the t-test for a single sample, just like that, you have to decide which step you're going to start with. If you're given raw data, then you need to start with step 1. Okay, if you need to get a variance and you need to get a difference mean, you need to start with step 1. If you are given S squared or S squared D or S of D bar, you can skip steps 1 and 2, move right on to 3. Move right on to calculating your standard error. So if I had already told you what S squared D was, you could move right on to here. Or if I had told you what SD was, you could move right on to here. And then finally, once you know your standard error, or if you're given the standard error, you can move on to this step. Okay. So again, it's a matter of how you're going to figure out which step to start with. Raw data, do steps 1 and 2. Already have a variance or a standard deviation, go to step 3. Already have a standard error, go to step 4. Okay. So let's look at an example together. We wish to know if people in the community of Moore, Oklahoma will have significantly different PCL scores 1 month after the tornado as compared to 3 months after the tornado. Notice how this is a repeated measures design. Right? We're interested in their score 1 month, and then the same people score again 3 months after the tornado. So we sample 16 people in Moore, Oklahoma who complete the PCL both 1 month and 3 months after the tornado. We obtain a sample mean difference, d bar, of 6 and a sample variance difference, s squared d, of 64. And we're going to assume our alpha is 0.05. So, null hypothesis, there is not a difference on average between PCL scores at 1 and 3 months in Moore, Oklahoma. Alternative hypothesis, there is a difference on average between PCL scores at 1 and 3 months in Moore, Oklahoma. And is this one-tailed or two-tailed? If you answered that it's two-tailed, you're absolutely right, because we use the word different here. We use the word different here. Had we said that the scores will be higher at 3 months, or had we said the scores will be lower at 3 months, it would have been one-tailed. Okay. But since no direction, it's two-tailed. So once again, we pull together all of our information. We were given that s squared d equals 64. We were given our n, our sample size of 16. We were given a difference mean of 6. And I also have this SD of 8. How did I get that? Well, if you realize that this is the variance, and that's 64, and then to get the standard deviation, I just take the square root of the variance, then you would see that this is 8. Because 8 squared is 64, or the square root of 64 is 8. Okay. And then finally, we have mu d. And remember, mu d always has the same value. And what is that value? 0. Yes, it's 0. So now we have to evaluate which steps have been completed and which ones we need to complete. Well, I can see that step 1 and 2 have already been completed. I have my d bar, which I would typically get in step 1. And I have my s squared d, which I would typically get in step 2. So what about step 3? Calculate the standard error of the difference mean, or SEM. Do I have that? Do I have S of d bar up here? Well, no. No, I don't. So that's the step I need to start with. I need to calculate my standard error of the difference mean. So here it is. And remember, I could have taken the square root of s squared d over the square root of n, or I could do it the way it's here. I'd get the same thing. I'd get the same answer. So since I set it up like this, I'm going to take 8 over the square root of n, or 8 over the square root of 16. Square root of 16 is 4, so it resolves to 8 over 4. And that resolves to 2.0, or really, I should say 2.0000. Okay. Step 4, calculate the t-score. So now I repeat carrying all this information over. I put in my mu d equals 0 because mu d always equals 0. And I put in my standard error of the difference mean to be 2.0000. Now I can calculate my t-score. I take d bar, or 6 minus 0, over my s of d bar, or my standard error of the difference mean, to be 2.0. And my df is n minus 1, or 16 minus 1. So I have my t-score is going to be 6 minus 0 over 2.0000. And my df is 16 minus 1, n minus 1. So that gives me 6 over 2, or 3, and a df of 15. Once again, I should probably say 3.0000. Okay. Now that I finally got my t-score, I could technically round. But there's a problem. I don't know what my raw data looks like, right? So I don't know how to round that number. So in order to apply the rounding rule, I would have to tell you, oh, all the original data or all the raw data had 1 decimal. And if I told you that, then you could round this to 2 decimals or 3.00. Okay. Now we get to look this up in our t-table. Okay. So the first thing we have to remember, was this a one-tailed or two-tailed test? If you recall, we said different, so it was a two-tailed test. Next, we have to recall our alpha. So we're on the right side with two-tailed test. Our alpha was 0.05, so we're down the middle. And finally, we have to recall our DF, which was 15. We're right here in this little blue shaded area on the right side. 2.132. That's the number we're trying to beat. That's the number we're trying to beat. So, does 3 beat 2.132? It sure does. It sure does. And because this was a two-tailed test, we don't have to worry about direction. We don't have to worry what's higher than what. We just know that 3 beats 2.132 because 3 is more extreme than 2.132. It's further away into the tail. It's further on the number line. Further away from the center. Okay. So in this case, we could go ahead and reject the null. And we could also say something else. We could say that the result is significant. The result is important because this was more, 3 was more extreme than 2.132. So we can say that it was significant and that we reject the null. Okay. All right. Well, that's all I have for you about the t-test for dependent samples today. Look forward to doing a sample, dependent samples that will be coming your way, a sample practice problem. And in the meantime, stay well, take care, and I'll talk to you next time.